So welcome back. So it's our great pleasure to have Professor Berndtsson from Chalmers University of Technology and the University of Gothenburg as our third speaker for this morning session and also last speaker for this morning session. He will talk about the convexity of Mabuchi K-energy and the uniqueness of extremal matrix. So let's welcome.
Thank you very much, and many thanks for the invitation to speak here. It's been a wonderful experience so far. Even more wonderful after I give my lecture, I guess. And also thanks for the award on behalf of myself and my co-author, Robert Bierman. Let me see. No? Yeah. It doesn't... what happens? Because you don't see it on the white screen, do you? But it doesn't really matter so much, but it works on... Yeah, but just the pointer. But just a pointer, I don't see that, but it doesn't really matter. I can point with my hand instead. You can see it? Ah, it's either. Okay, fine. Okay. Okay, amazing. Okay, so as the title suggests, this talk will be divided into two parts. The first is about the convexity of the Mabuchi K-energy, and the second is about uniqueness of extremal metrics. And in fact, I will concentrate on the case of metrics of constant scalar curvature, which is a special case of extremal metrics. So this is about the differential geometry on complex manifolds. And let me give first then a little bit of the setup. So we have a compact Kähler manifold of dimension n, x omega. And then the so-called Mabuchi space, which has already been discussed in several lectures before here, is a beautiful H of x and omega. It's a space of all functions u in C infinity, such that if you form a new Kähler form by taking the original one and adding I d d bar of u to that, you still get a positive form. So you get a new Kähler metric. And this will be designed omega u. And then if you mod out the constants, given omega u here, u is uniquely determined up to a constant. So if you mod out the constant, you just get the space of all such forms, of all such Kähler forms. So you get the class of all Kähler metrics in the same cohomology class as omega. That's what I have there. Now, this space here is an infinite dimensional Fréchet manifold, which sounds very abstract, but it's actually not so bad because it's just an open subset of the Fréchet space of all smooth C infinity functions. So this is called the Mabuchi space, and it plays a big role in the discussion later on. Okay. Now, Mabuchi made this into a Riemannian, infinite dimensional Riemannian manifold by introducing a Riemannian metric on H. So the norm squared of a tangent vector, u dot, I should say that its tangent space at any point u, it can be identified with the space C infinity there, because it's a tangent space of this space here, which is the space itself, since it's a linear space. So you introduce a Riemannian metric by letting the norm squared be equal to just the L2 norm here. So u dot now stands for an arbitrary C infinity function, and the metric depends on the point because you're taking the norm with respect to the volume element omega u. Now, you can define then geodesics in this space in the standard way of differential geometry. And it turns out, it's a well-known fact that I think is due to Semmes and Donaldson, that you can describe them in a way that involves the complex Monchampère equation. So first, it is a real curve. T is a real variable. You map it into ut that lies in H there. You get ut. It's a curve of functions. And you can make it into something that depends on a complex variable tau instead of a real variable by just letting it be independent of the imaginary part of the variable. So then you get a function capital U of tau and x. And a geodesic should satisfy two things. First, it should be it should be omega plurisubarmonic. So if you take I dd bar of this function capital U here with respect to all of the variables x and tau, so one dimension more, it should be non-negative. And it should satisfy the homogeneous Monchampère equation. So if you raise this form here up to the power n plus 1, then you should get 0. That's what it turns out to be a geodesic in this paper, it means. Now, in the study of Kähler metrics in a given cohomology class, which is precisely what we have here, there are a certain number of functionals that play an important role. So I call a typical functional f here. It's just a map from H to R then. And they are often defined somewhat indirectly by first defining the differentials. You take the derivative of, you take the differential of f, apply it to a tangent vector. That's the same thing as ddt of f of ut. And you say what that is. So the first example, I guess, most basic example, very important, is the Monchampère energy. You take ddt of E here is just the integral of U dot with respect to this volume element, omega un. And you normalize also by the volume of the Kähler class. This does not depend on omega. Does not depend on U. Of course, you have to check that this recipe really gives you a function, because what this says somehow is that this defines a linear function on a tangent space with a one form, but you have to prove that that one form is actually closed in order to know that it is the differential of a function. But you can do that, and then you have the definition of the energy. Now, in this talk, there is another energy function that plays an even bigger role. But before I come to that, I come to a modification of this Monchampère energy, and that's just obtained by taking an arbitrary 1-1 current closed, so that's T. And then we take the same recipe, we say that the differential of E sub T, the relative Monchampère energy, would be precisely the same thing, but so to speak, on T. So you just raise this to the power omega u to the power n minus 1, and you wedge it with T. That's the relative Monchampère energy. It probably has some other norm also. So if you think of T as being the current of integration on a submanifold of X, then this would just be the standard Monchampère energy on that submanifold. So that's how it works. Now, Mabuchi's K-energy, which is the main actor in the first part here, is defined by saying that the differential of M should be given by this, U dot, the integral over there, where S is the scalar curvature of the metric omega U. So again, you have to prove that this really defines a function. And S hat U is the average of the scalar curvature. And this turns out not to depend on does not depend on U, certainly. And the main point here, there are two main points actually in the definition of this Mabuchi K-energy. One of them is that the critical point of this functional, by definition, is precisely the points where S minus S hat is equal to 0, so the scalar curvature is constant. And the origin of this is the Futaki invariant. So Mabuchi developed this starting from the definition of Futaki's famous invariant. Now, you see that given this, the question of existence of uniqueness of CSC metrics, that is metrics of constant scalar curvature, it can be translated to questions about this function M here. They're just the critical points of M. So are there critical points of M, and are they unique? Okay. And the following theorem, basic theorem, is due to Mabuchi here. He computed the Hessian of this of the K-energy. So that's what I call H sub M there. And it's equal to the L2 norm of a certain object. Beautiful D sub T, depends on T, apply to U dot, and you take the L2 norm of this. And this D is a certain differential operator that I'm not going to write down, but it has an important property, well, that I will come to later, actually. The main point for the moment is just that this thing here is obviously non-negative. So, as a consequence of that, the second derivative of the K-energy along a geodesic is equal to the Hessian acting on the tangent vector, and that's non-negative. So it means that this function M here is convex along geodesics. And that fits even better than with the picture I had before, as explained very much by Thomas Darvas in his lecture, that if you want to find critical points, it's very nice to have a convex function. So you need to, in order to prove that there are metrics of constant scalar curvature, you want to prove a certain properness of this function, and then it's good to know that it's convex, and the same thing goes for uniqueness of such things. So it looks like it's a rather simple problem than the problem of analyzing metrics of constant scalar curvature, because you have a convex functional and you just want to study the existence of critical points. But there are, of course, several difficulties. As a matter of fact, the problem is not completely solved yet, but, well, up to some point it is. One problem that I will address here is that in order to apply it, you really need to have a lot of geodesics. If there are no geodesics, the fact that it's convex along geodesics doesn't really say very much. So in particular, it's known that you cannot always connect 2 points in H by a smooth geodesic. So, but there is a substitute for that says that morally you can connect any 2 points in your space by a smooth geodesic. And that says that you can connect them by a generalized geodesic. And that's defined as a bounded curve of functions. A curve of bounded functions such that the corresponding capital U there still satisfies the same thing, that I d bar of this is greater than or equal to 0, so it's omega plurisobharmonic. And moreover, it should still satisfy the Monchampère equation. So that uses the theory of Bedford and Taylor, which says that you can actually define the Monchampère operator on bounded functions. And now there is a fundamental theorem of Chen that says that you can connect any 2 points in this Mabuchi space, by a generalized geodesic. But the drawback of this is that U of t does not necessarily lie in the space. You don't know, at least, if it lies in the space, because it's just a bounded function, and you don't know that it's strictly plurisubharmonic on the space X. So this poses some problems, and in particular, the problem that I'm going to discuss is whether M is the Mabuchi K-energy is still convex along such generalized geodesics, because that would be more useful in practice then. But philosophically, I guess the main ingredient here is Mabuchi's theorem. Okay. Now, the first problem is that it's not even clear how to define the K-energy if you just have a generalized geodesic, because it used things like the scalar curvature of the metric, and if the metric is not smooth, I mean, how can you define the curvature and the scalar curvature? But this was overcome also by Chen, who approved the following formula for the K-energy. So the formula I written there, in order to write it down, you start with an arbitrary smooth volume form that I call mu on the manifold, and you let T be the current IDD bar of log U. So log U is not really well defined, but IDD bar of log U is well defined because it doesn't depend on the choice of coordinates, as long as they're holomorphic. And then it turns out by computation that M of U you can write it like this. It's the logarithm of omega U to the power n divided by mu. So this is the reason why we introduced the mu. We would like to write logarithm of omega U to the power n, but we cannot do it because it's not a well-defined function. But when you divide it by mu, it works. And then we compensate for the introduction of mu by adding this relative Monchampère energy sub T, where T is this IDD bar of log U. And then there is a term which is just the standard Monchampère energy. And they are multiplied by certain constants that you can write down explicitly, but they will play not such a big role here. So I don't care about them. And using this formula, you can define the Monchampère, you can define the Mabuchi functional along a generalized geodesic, because by Chen's theorem, this form here, it has bounded coefficients. It's well defined almost everywhere. So this omega U to the power n is an object that exists almost everywhere. You divide by mu, everything. You might worry that this is zero, could be zero. You get minus infinity, but then it's killed by the omega U to the power n there. So no worries. It really works. So then you have the question, yeah. So this is answered, the obvious question is answered by our theorem then. It says that M is convex along generalized geodesics. And I would like to say a few words now about the main idea of the main idea of the proof. Just check here, I'm doing it for time. Yes. So I will sketch the proof without any details. So you go back to the formula. I want to prove that this function is convex along geodesics. It's a classical and relatively elementary fact that this function here is actually linear along geodesics. So we don't need to worry about that. So those are the two terms that we worry about. And now I'm going to write down then the main difficulty of those is the first term here, which is the logarithm term. This is sort of the entropy. My co-author, Roberts, who knows, well, at least claims to know a little bit of physics, he says that this is like energy and this is like entropy. And in comparison with thermodynamics, this should be called the free energy of something. So at any rate, it's the entropy term here that's the main difficulty in the argument. So in order to attack this, we define a 1-1 current by taking this function u and taking IDD bar of that, we get the 1-1 current, and then we add the fixed Kähler form omega there, and we get a 1-1 current on x multiplied by a strip. And now, the first term here, you can see that it is really equal to, we want to take, the first term here is what you get when you restrict this thing here to a fiber. You fix the value of tau, and then you get the fiber, a copy of x there. You just get the IDD bar of u in the x direction, and then this will be omega u. So the first term in our formula is the fiber-wise integral of this form. But the fiber-wise integral, in the language of complex analysis, you can think of that as a push forward of currents. So you have your big space here, x. So here is, so this is x. This is my Kähler manifold, slightly simplified picture. And then I took the multiple, I multiplied it by c with the variable tau here, and this is x. So this is a picture of x times tau. X times c, variable tau here. And we're looking at this total space here. And I fix the value of tau there, and then I get the fiber here. I want to take the integral of something over there, and I realize it as a push forward of this map pi, which is the projection from this total space and down to c. This is pi. Now there is a in order to prove the convexity, you want to compute it's enough to prove that M is subharmonic because it depends only on the real part of tau, and then subharmonic and convex would be the same thing. So you want to compute the DD bar of this, and the nice thing with push forwards is that it actually commutes with the DD bar operator. So you get three terms here. You get the push forward of this, I DD bar of log omega u to the power n, which we had before. And then you get the same thing for log u, and then you get I DD bar of this, of e sub theta. So I claim that the last two terms, they cancel out. This, of course, you can check by computations, but it's almost philosophically obvious that they must do that because u is completely arbitrary. You will get the same thing independent of what u is. So therefore, I think it's very reasonable that the last two terms would cancel. So you really need it's only the first one that you're interested in. You want to look at this. So we have the push forward of this form, of this current here. So in order to prove that the push forward is positive, it's enough to prove that this is a positive current on the total space, this thing here. Now, when ut is a genuine geodesic, this, you have the following picture. Then you look at this form omega u, and it depends on tau also. So the hypothesis on a geodesic is that this omega here has exactly one zero eigenvalue, and all the other ones are positive. So it gives rise to a sort of foliation of the total space like this. These are the leaves defined by the zero direction of this 1-1 form. And what the claim is in that case is precisely that this function log omega u to the power n there is subharmonic along the leaves. That's what it says. This will actually be equal to the Laplacian, so to speak, or the IDD bar of this function, restricted to a leaf, and then you sum over all the leaves there. So the claim is that it's subharmonic along the leaves. And that's a classical fact that was discovered long ago by Bedford and Berndtsson. And the crux of the proof is to generalize this to non-generalized, to non-smooth geodesics. The problem, of course, is that there is no such foliation or anything, so we cannot do the same thing. So then what we do instead is that we use the Bergman kernel. So we take a little, I want to prove that a certain current is positive. It's a local property, so I take a little coordinate neighborhood here, which is like a ball in n+1 variable. And I can take the Bergman kernel on that ball. So I'm a little bit sloppy here, but I choose coordinates on the ball, and then I just have a standard ball in Cn+1, and I can take the standard Bergman kernel there. And this Bergman kernel, I get, yes, that's what I write here. That's the Bergman for each fiber T here. I should have written a tau maybe, but it doesn't depend on the imaginary part. So you look at, you take the Bergman kernel for the weight e to the minus k phi t, and you multiply by this thing there. It's a standard fact about the Bergman kernel that it's a plurisubharmonic function for each fixed value of t here. And there's another standard fact, which is a very nice fact, and that's Bergman kernel asymptotics. So Bergman kernel asymptotics says that if you take this Bergman kernel and you multiply it by this weight function, e to the minus kt, and you let k go to infinity, this will go to, yeah, I write it as this. This is an NN form, but given the coordinates, I identify it with the function. So then it goes to the determinant of the Hessian of this phi. So this is the thing that I was integrating. So I can replace it now by the Bergman kernel and then pass to the limit. So if I replace it by the Bergman kernel, I get this, and then I get this thing here by when I take logarithm of that. I get minus this thing, minus k omega. Now, there is an older theorem of myself, which was actually my entrance ticket into the field of complex geometry in a certain sense, which says that this function here, this is not just plurisubharmonic for each fixed tau, tau, but it's actually plurisubharmonic as a function of all the variables of tau and on x at the same time. So this thing here will be positive. And that's almost what we wanted, except that we have this term here, which looks very bad because it has a minus sign and it's negative, and that looks bad until you remember that you have a geodesic. And the geodesic equation says exactly that this thing here gives no contribution. It vanishes when you take the wedge product. That's precisely the geodesic equation. So therefore, that proves that if you replace log omega u to the power n by the Bergman kernel, you get something positive, and then you pass to the limit, and that's basically the proof of the theorem. Yes. So that was the first part then. Now I still have time to say a few words about uniqueness of Keller, of metrics of constant scalar curvature. Yes. So it's actually about extremal metrics, but I will not even define them. I will just look at metrics of constant scalar curvature. And there were previous works in that direction. First, there was a paper by Berndtsson in 2001, where he proved uniqueness of metrics of constant scalar curvature in the case when the Keller class was integral and the manifold had no holomorphic vector fields. And then there was a paper of Mabuchi that generalized the method of Berndtsson to the case when there are holomorphic vector fields, but the Keller class is still integral, so you're still in the projective case. And then there was a paper of Chen and Tian that claimed the complete theorem in full generality, but there were some issues with that paper. Some claims about some technical lemmas that made it a little bit doubtful. At any rate, I would want to emphasize also that our proof is actually fairly simple. The other papers were probably more complicated. In particular, Chen-Tian paper is over 100 pages. So now that we have the convexity, I want to prove uniqueness. So let's say that we have two metrics of constant scalar curvature. Here is one, and here's another one, and they lie in Mabuchi space. So I connect them with a generalized geodesic. It goes like this. Then I look at M here, beautiful M. The Mabuchi K-energy is a convex function, and it is, the derivative is 0 here because it's a CSC metric, and the derivative is 0 there, and so it actually has to be constant because of the convexity. That's the main point of the argument. But it's not enough because there is no saying that the Mabuchi K-energy is strictly convex. So it might, actually it isn't if there are holomorphic vector fields at least, but it isn't in any case, really strictly convex. So this argument is not quite enough. It doesn't look very constant. It should be constant, this function that I draw there. Okay, so there are some difficulties involved in this, in carrying out the proof because of the lack of strict convexity. So therefore, I will say a few words about, maybe I emphasize those technicalities, not only technicalities, but there's a certain point I want to emphasize because actually when I reread our paper, I found it, both Robert and me found it rather confusing. So let's see if I can do it better here. You know? You take a holomorphic vector field on X here. And we can contract a certain Keller form, omega, with V here, and then we get a closed, D-bar closed 0, 1 form there. And then we define now the space, this old German H, as the space of all holomorphic vector fields that are such with the property that this form here is D-bar exact. So it has a potential. It's sort of the complex analog of a Hamiltonian vector field, but you have a D-bar operator instead of the D operator. The connection with Mabuchi's formula is very important here. This defines a holomorphic vector field. A certain function here, H, you can always do this. For any function, you can take D bar H. You can define a vector field by this formula, but it's not always holomorphic. And the condition that is holomorphic is precisely that this function H here satisfies the differential equation, beautiful D of H is equal to 0, where D is the differential operator that occurred in Mabuchi's theorem. Now, the point is that this space of vector fields here is actually closed under Lie brackets, so it defines a Lie subgroup of the group of all automorphisms of X. I skipped the next part here. And the theorem is that if we have two CSC metrics, there is an automorphism that lies in this subgroup of all automorphisms that brings one to the other one. So you have uniqueness of CSC metrics up to automorphisms, and not even all automorphisms are needed, but only the automorphisms that lie in this subgroup, or so to speak, complex Hamiltonian vector fields. How much time do I have left here, do you think? Less than 10 minutes? Yeah. Okay, fine. I think I can do it. With some luck, yeah. So let's start with the case when H is equal to just the identity element. So there are no holomorphic vector fields in this class. The basic idea is still that you connect the 2 points with a generalized geodesic. You still have the same picture there. Yeah, that's what I said before, that you get this function here has to be a constant, but we cannot really conclude. Okay, so what do I do then? So one way is that we perturb the functional. So we consider a more general, we consider a perturbed version of the functional. So we put M sub S is equal to the Mabuchi functional plus S times F, where F is some other functional. The precise choice of it is not really so very important, but it should have the property that it should be strictly convex on Mabuchi space. So we make it strictly convex by adding a small positive, S should be positive, multiple of some strictly convex function. Okay, and then the idea is, so then I look at MS instead. And then here's a constant scalar curvature metric, and here's another one. Then you can apply the implicit function theorem. For S equal to 0, yeah, you say that D, the derivative of ms is equal to ugly ms, and the derivative of f is equal to ugly f. So now you have that m0 at the point omega 0 was equal to 0. So this was a critical point, so the derivative is equal to 0, and the same thing for m0 omega 1. But then you apply the implicit function theorem. So you take a small curve of metrics that start here and start there, and that are critical points for this. If you accept that the implicit function theorem works, then you will get critical points for the functional beautiful ms in a neighborhood of here. But now the functional is strictly convex. So, and it's a critical, the derivative is 0 here and 0 there, so it has to be constant. And since it's strictly convex, this is only possible if those 2 points coincide. And since that is true for all small s, those also have to coincide, then you're done. So that would prove the uniqueness in that case. It actually does prove the uniqueness in that case. It does prove the uniqueness in that case in case when there are no holomorphic vector fields. That's enough. The argument is enough in that case. In the general case, it cannot really work because then you only have uniqueness up to holomorphic vector fields. So I will skip that. Now, so let's just say a few words about the general case then. You need an additional twist when you do have holomorphic vector fields. And the reason is that then the implicit function theorem does not apply anymore. The hypotheses for the implicit function theorem are not satisfied. So then there is a preliminary step in that case that the hypothesis does not imply, but there is a preliminary step that says that you can apply an automorphism, you can move this one by an automorphism to another one, such that up there the hypothesis of the implicit function theorem works. And then you move another one, you move this one with another automorphism to there. And then you can do the same argument and prove that those two have to be the same. And that is what proves the uniqueness up to automorphisms in that case. Okay, so that's basically the content of the talk then. Just a few words about some extensions of this. That Darvas introduced a scale of Finsler metrics on Mabuchi space by replacing the L2 norms here by LP norms. In particular, the case p equal to 1 is very interesting. And you can look at the completion of the space of H under this metric. And those turn out to be, for the specialist, scalar potentials with finite p energy. And he proved that any 2 points in the completion can also be connected by some sort of generalized geodesics, a finite energy geodesics. So they play an important role in the existence problem for CSCK metrics. So first was a later work by Berman, Darvas, and Liu, where they showed that the K energy is actually also convex along those more generalized geodesics, the finite energy geodesics. And then they could also prove that any minimizer of Mabuchi K-energy in this space, the completion of H under the L1 norm, is any minimizer of the Mabuchi K-energy has to be smooth. And that was under the assumption that you know that a smooth CSC metric exists in a given cohomology class. So The proof followed the same scheme once you know these properties, this extension of the convexity theorem to less general geodesics. And together with the earlier work of Darvas and Rubinstein, they could prove that if a CSC metric exists, then M is proper modulo automorphism in a certain sense. And this confirmed the conjecture of Tian. So then you have to apply the convexity theorem not only to geodesics between 2 points, but also to geodesics that go out to infinity, so-called geodesic arrays. And the converse of this result was recently established by Chen and Cheng. So they were really able to prove that minimizers of the Mabuchi K-energy are always smooth without this extra assumption up there. And all this has together led to the theorem that characterizes the existence of CK metrics in terms of properness of the Mabuchi K-energy. So what seems to remain in this area then is to translate this analytic condition of properness of the K-energy to the algebraic condition of stability. And there are rumors that recent work is on the verge of actually doing that, which would then close the proof of the so-called Yao-Tian-Donaldson conjecture in the general case. Thank you very much.
Thank you. Very nice talk. So, any questions or comments? So maybe I have two questions. So the first one is about, so you said the CS metric is somehow modulo the automorphism group. So actually there are automorphic group of X and also the reduced or linear automorphic group of X, right? So
I think the reduced group is isn't that what I called the one that I described that had corresponded to the Lie algebra of all vector fields that were, so to speak, complex Hamiltonians. I think that is it. Yes. So it's unique up to this group, not only up to automorphism, all automorphism.
Up to the, you mean
up to
the whole automorphic or the linear automorphic group?
If I understand your terminology, linear group, it's up to the linear automorphism.
Linear group. So it somehow acts on the set of the CS K metric transitively, right?
Yes.
Okay.
Yes. Exactly.
So also concerning your last slide, so I think there are also a version of the non-Archimedean K-energy version, right? So that can be obtained by just the identification of the complex manifold. Then you can do the non-Archimedean K-energy on such kind of space like Berkowitz identification space.
I am not competent to. I don't know if that has. I don't think it has been done, and I don't. And I don't know if it can be done, but yeah.
So also, I mean, by the non-Archimedean the K energy. So is that also possible to characterize the K stability of some variety?
Again, I don't know that, but
okay.
but there are definitely many people. There's a lot of work in that direction which I haven't followed. I mean, that's the work of Berndtsson and Johnson and Hashimoto. Yeah, Hisamoto, no? Yeah.
Okay. So, any more questions or comments? If there are no further questions, so let's thank the speaker again. Thank you.